Yesterday, you worked on an introduction activity to systems of linear equations, or sometimes we just call them systems for short. If you have not corrected that activity yet, it would be a good idea to go and do that before you watch this video, because there are going to be some references to that activity in the second part of your notes for today. Yesterday's activity, the introduction at the top of the page, very quickly told you what a system of equations is, or a system of linear equations. So system of linear equations is a comparison between two different linear equations. And one way we can compare the equations is by putting them on a graph, which is what you were doing yesterday and what we're going to talk about here in a few minutes. Similar to how you can solve an equation, so if I gave you an equation and said solve this equation, you would know what to do because we've been doing that this year. You could also solve a system of equations. We're going to talk a little bit about what that is. So yesterday, your activity, one of the things that happened with one of your graphs is that the lines intersected each other. So the solution or the answer to a system of linear equations is the point of intersection of the lines when you graph them. So if you graph them and put them on or if you graph them both, you look and see where they cross, and that is your solution. So the solution to the system of linear equations is the point of intersection of the lines. In other words, it's where the lines cross each other. So if somebody said to you, solve this linear equation, solve the system of equations, if they say solve a system of equations, what they're really saying is find where the lines intersect. So solving a system of equations is the process of finding the solution, which is where the lines cross. So this is an example of that. So this is a problem that says solve the system of equations by graphing. And on your notes, your equations are kind of off to the side here. Mine is formatted a little bit differently, but these are our equations. So since the solution to the system of equations is where the lines cross, we need to put both of the lines on the graph so we can see where they cross. So our top equation has a y-intercept of 2. And it has a slope of -3. So -3, remember, is -3 over 1. So if you're thinking rise and run, up and down and over on the graph, that would be telling you to go down 3 and over 1. So we're going to zoom this in a little bit to make it easier. So down 3 and over 1. And we can do that as many times as I want. Down 3 over 1, down 3 over 1. I could even go backwards, up 3 and backwards 1. So if you're running out of room on your graph, you can do that. But this is where that line's going to fall. So now we have to do the second line, 2x plus 7. So that equation has a y-intercept of 7, and it has a slope of 2, 2 over 1. This time the slope is positive, so we would go up 2 and over 1. So up 2 and over 1. I can only get 1 point on the graph before I'm going to go off the graph, but I could go backwards too. I could go down 2 and backwards 1, so I could reverse that. And if I do that, I'm actually going to see where the lines cross if I extend it backwards just a little bit. So don't be afraid to go backwards with the pattern if you need to. So the lines are crossing at that point right there. So the point where they cross, if we grab that coordinate, so that coordinate is -1, 5. So if you were told solve the system of equations, the solution to this system of equations is -1, 5, because that's where the lines cross. Now, a little bit more about what that means. So we figured out the answer here. It's -1, 5. A correct solution, so if you're thinking, well, did I graph them right? Is my answer right? I'm not sure. You actually have a way to check. A correct solution should make both equations true, which makes sense because that point right there is on, at the same time, is on or part of both of the lines. It's part of the line that's going down because it's on that line. It's also part of the line that's going up because it's on that line. So if it's on both lines, it should make the equations for those lines work correctly. So you can actually check your answer by filling it in, and you have to test both equations. If you only test one equation, then you don't know if you're right because it has to make both equations work. And the only way to find out if they both work is to test them both. So we can take our answer, -1, 5, remember this is x and this is y, and drop it into the x and the y in our equation. So if we do that, our y equals -3x plus 2 turns into a 5 equals -3 times -1 plus 2. We can track that through and see if it works. -3 times -1 is 3. 3 plus 2 makes 5. So that equation works. But now we have to check the other equation because it has to make both equations work, not just one of them. So you have to test both. So if we drop our answer into the y equals 2x plus 7, that turns into 5 equals 2 times negative 1 plus 7. 2 times negative 1 is negative 2 plus 7. Negative 2 plus 7 is 5, which is what it's supposed to equal. So check, check. They both work, which means that is the correct answer. So that is how you solve a system of equations. One way you can solve it is by putting it on a graph and seeing where the lines cross. Now, yesterday's activity, you figured out that, or you saw some examples that the lines don't always cross nicely like they did in this problem. So when you're working with systems of equations, you have to be aware of that. There are actually 3 different types of systems. So the type we were just looking at is a type that has one solution, which means you're going to get a coordinate for your answer. So you would have something that looks like that for your answer to that. So on the graph, it's going to look like 2 intersecting lines. Now, in order for the lines to intersect or to cross each other, they have to be going different directions. So if they're going the same direction, they won't cross. So we have to think for a minute about what makes the lines go different directions. Well, that would be the slope, because the slope controls the steepness of the line. And if the lines are 2 different steepnesses, they're going to go different directions and they will cross somewhere. So a way you could tell just by looking at the equations what's going to happen is if your equations have different slopes, then you know you're going to have one answer somewhere, because different slopes means they're going different directions, and if they're going different directions, they're going to meet up somewhere. So that was one type. Now the other type, you saw 2 other types in your activity yesterday. So you saw a graph where, we're actually going to kind of go backwards through this, where you had identical equations, so both equations were the same. So identical equations would be the same slope and the same y-intercept. So same slope and y-intercept. So same everything, identical in every way. So on the graph, that looked like a single line. So there actually was 2 lines there, but the lines were directly on top of each other, so it just looked like one line. So that's not going to have one answer. That's going to do something different. We have to think for just a minute. So we just said that the answer to a system of equations, or the solution, is where the lines cross or where the lines touch. So if I take a line and I put another line directly on top of that, the lines are touching everywhere. They touch here and here and here and here and here and here, and you could keep going. They're on top of each other. They're touching all the time. So that means that there is an infinite amount of places where those lines touch each other. So there's not just one solution. There are infinite solutions because the lines are touching everywhere. So if you get into a situation like that, where you have identical equations and the lines are on top of each other and it looks like a single line, then your answer wouldn't be a coordinate. You would just say infinite solutions for your answer. Now, the last type you saw in yesterday's activity was the graph where we had parallel lines. So parallel lines never touch. And if the answer is where the lines cross or where they touch each other, if they never touch, then I can't have an answer. So parallel lines, there is no answer because the lines never touch. So you would just say that there is no solution. Because there's no intersection point. The lines will never meet up. Oops, sorry, no solution. So if you have a parallel line situation, then your answer, if it said solve the system of equations, but they're parallel, then for your answer, you would say no solution. So you could have one solution, in which case you would name it and say what the coordinate is, kind of like we did up here, -1, 5. You could have lines that are right on top of each other. They're the same line, in which case your answer would be infinite solutions, or you could have parallel lines and your answer would be no solutions. And then on the, this came up a little bit in your notes. I noticed several of you guys came up with this on your own, and it was also on the answer key. But if your lines are running parallel, they have to be going the same direction. So that means they have to have the same slope, because the slope controls the direction of the line. But what's making them not be in the same place is that one is higher or lower than the other. So they have different y-intercepts. So that is a little bit about what it means to solve a system of equations and how you do that, and also what are the different things that can happen when you try to solve a system of equations. So for your assignment today, you are actually going to try practicing solving some systems of equations. So you're going to try and put them on the graph, and if they have an answer, one answer, you'll tell me what the answer is. Or if it's infinite solution or no solution, then you'll tell me this is infinite solution or this is no solution.